February 17th, 1944. Dawn light breaking over Truk Atoll in the Caroline Islands. Lieutenant Commander Robert Moriya stood on the bridge of the destroyer Nowaki, watching American carrier aircraft swarm like hornets over what Japan called the Gibraltar of the Pacific. His orders were simple: escape, get the critical documents and personnel aboard to safety before the Americans could intercept them. What Moriya didn't know, what no Japanese naval officer fully understood yet, was that this wasn't just another battle. This was the moment when an invisible technological chasm would reveal itself in the most brutal way possible. A chasm measured not in inches of armor or caliber of guns, but in something far more deadly. Radio waves bouncing off metal, translated into precise firing solutions faster than any human eye could track. 40 miles northwest of the lagoon, USS Iowa and USS New Jersey spotted Moriya's ship through the morning haze. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The range was 35,700 yards, over 20 miles, beyond the visual horizon, beyond what any navy in history had considered a practical firing distance. But the American battleships opened fire anyway, and their first salvos straddled Nowaki perfectly, shells landing on both sides of the fleeing destroyer. Moriya watched the towering splashes bracket his ship and felt something close to disbelief. How could they possibly aim that accurately at such a distance? The answer sat atop Iowa's fire control tower, a rectangular antenna. The Mark 13 fire control radar, a device that could track both the target and the fall of the ship's own shells, with precision that made optical rangefinders look like children's toys. The Americans were quite literally seeing through the fog of war in ways the Japanese couldn't imagine. But here's what makes this story devastating. It wasn't that Japan lacked brilliant engineers or skilled sailors. Their optical rangefinders were among the finest in the world. Their crews trained relentlessly. Their fire control computers, the Type 92 Shagekiban, could calculate complex ballistic solutions. What they lacked was something more fundamental: the industrial capacity to turn radar from a laboratory curiosity into a weapon that worked under combat conditions. And by February 1944, that gap had become a death sentence. This is the story of how American radar fire control didn't just give the Navy an edge. It rewrote the rules of naval warfare so completely that Japanese commanders spent years afterward trying to understand what had actually happened to them. Because when you can hit what you cannot see, when you can fire accurately while maneuvering at flank speed, when you can fight at night as effectively as in daylight, you're not just winning battles. You're fighting in a different dimension entirely. The Japanese believed they understood modern naval warfare. They had pioneered carrier tactics at Pearl Harbor. Their long-lance torpedoes were the best in the world. Their optical fire control systems, built on decades of British and German expertise, could measure range with extraordinary precision. The problem was that all of these advantages assumed one thing: that both sides were playing by the same rules, that engagement ranges would be dictated by what human eyes could see and human hands could measure. By 1944, that assumption was dead. American battleships and cruisers had something the Japanese didn't: full blind-fire radar capability, the ability to detect, track, and engage targets without ever seeing them. The Mark 8 and Mark 13 fire control radars could spot 16-inch shell splashes at ranges exceeding 35,000 yards, in darkness, through smoke, in rain squalls and fog. While the firing ship maneuvered at high speed, the implications were staggering. Consider what this meant in practice. A Japanese battleship captain using optical rangefinders needed clear weather, good visibility, and a relatively steady platform to get accurate readings. His fire control team had to manually observe the fall of shot, estimate corrections, and relay adjustments to the guns. Even with Japan's excellent optics, visual spotting deteriorated rapidly beyond 18,000 yards. The shells simply became too distant, too small against the vastness of the ocean to track reliably. Beyond 25,000 yards, optical fire control was essentially guesswork. Now compare that to what an American fire control radar operator saw. On his screen, the target appeared as a clear blip, range accurate to within yards. bearing precise to fractions of a degree. And when his ship's guns fired, the radar could track the shells themselves, painting their splashes on the screen like someone had drawn them on paper. The operator could see instantly whether the salvo fell short or over, left or right. No squinting through spray-coated binoculars. No trying to distinguish shell splashes from whitecaps in rough seas. Just clear, immediate, actionable data. The Japanese Type 22 radar, their best surface search set by mid-war, could detect large ships at 35 kilometers. Respectable performance for its day, but it wasn't designed for fire control. It couldn't provide the angular accuracy needed for gunnery solutions. Japanese fire control still depended on optical rangefinders feeding data into their mechanical computers, which meant they were still fundamentally limited by what human eyes could see and human judgment could interpret. Even Yamato, with her massive 15-meter rangefinders mounted high above the waterline, was blind compared to an Iowa-class battleship's radar. The American Mark 38 gunfire control system represented the apex of analog computing integrated with radar technology. Two complete systems, forward and aft, each independent, each capable of controlling the ship's 9 16-inch guns. The director high on the superstructure housed a 26.5-foot stereoscopic rangefinder for backup, but the real magic sat in the plotting room below decks. The Mark 8 rangekeeper, a mechanical marvel of gears, cams, and servo motors that created a constantly updating model of the engagement. It tracked the target's bearing, range, speed, and course. It compensated for the firing ship's own movement, for wind, for the rotation of the Earth, for the curvature of the projectile's path. All automatically, all in real time. A single operator could control this system, adjusting variables as needed. Compare that to the Japanese Shaga Kiban, which required 7 operators and extensive manual input for every calculation. The American system could keep a firing solution on a target, while the Iowa-class battleship executed high-speed turns. Tests in 1945 showed USS North Carolina maintaining accurate fire during a series of back-to-back 450-degree turns, followed by 100-degree turns. The ship was essentially driving in circles at high speed while keeping her guns on target. No Japanese fire control system could do this. They lacked the gyroscopic stable elements that allowed American systems to compensate for the ship's maneuvers. A Japanese battleship had to steady up on course to maintain accurate fire, which meant choosing between shooting and dodging. American ships could do both simultaneously, but perhaps the most critical advantage was this. American radar fire control worked at night. USS Washington proved this on November 15, 1942, during the naval battle of Guadalcanal. In complete darkness, without searchlights, Washington detected the Japanese battlecruiser Kirishima at 8,400 yards and opened fire. 9 16-inch shells out of 75 found their target, a 12% hit rate in pitch blackness against a maneuvering capital ship. Kirishima, her fire control teams, blinded by darkness, never knew what hit her until shells began tearing through her superstructure. She burned, exploded, and was scuttled by her own crew. This wasn't a duel, it was an execution. Japanese naval doctrine had emphasized achieving superiority at long ranges through superior optical equipment and intensive training. But doctrine written for a world of visual rangefinding meant nothing when the enemy could see in the dark. Every tactical assumption, every training evolution, every careful calculation of engagement ranges, rendered obsolete by a technology Japan couldn't match. Not because they didn't understand the principles, they did, but because building reliable, combat-worthy radar fire control systems required an industrial base Japan simply didn't possess. Manufacturing the magnetrons for centimeter wavelength radar demanded precision that Japan's war-strained industry couldn't consistently achieve. Quality control systems to test and verify each unit, spare parts and replacement components in sufficient quantities to keep systems operational. Trained technicians who understood not just how to operate the equipment but how to repair it when it broke. The Americans had all of this. Japan had some prototype systems, a handful of radar sets that sometimes worked, and a growing sense that they were fighting an enemy that could do things they couldn't. But the full implications wouldn't become clear until battles like the one about to unfold off Samar. October 25, 1944. Dawn off the Philippine island of Samar. Vice Admiral Takeo Kurita stood on the bridge of the battleship Yamato, the largest and most powerful warship ever built. Around him steamed 4 battleships, 6 heavy cruisers, 2 light cruisers, and 11 destroyers. Center Force, the most powerful surface action group Japan had sent to sea in months. Their mission was to break through to Leyte Gulf and destroy the American invasion fleet. At 0637, a lookout spotted masts on the horizon. Kurita believed he had found Admiral Halsey's fast carriers. The decisive naval battle Japan had dreamed of seemed within reach. He ordered a general attack. His ships surged forward at flank speed, main batteries training toward the distant targets. What Kurita had actually found was Taffy 3, 6 escort carriers, 3 destroyers, and 4 destroyer escorts, ships designed for anti-submarine warfare and close air support, not fleet actions. Their escort carriers could barely make 18 knots. Their destroyers mounted 5-inch guns that couldn't penetrate cruiser armor, let alone battleship plate. They were hopelessly outmatched. By every measure of naval power, displacement, armor, firepower, speed, Taffy 3 should have been annihilated in minutes. But something strange happened. The American ships didn't die on schedule. Rear Admiral Clifton Sprague ordered his carriers to run south, making smoke, launching every aircraft they could get airborne. His escorts charged the Japanese formation, firing torpedoes and anything else they had. Seemingly suicidal attacks that should have been swatted aside by overwhelming Japanese firepower. Except the Japanese fire wasn't overwhelming. It was erratic, inconsistent. Shells that should have obliterated the escort carriers instead fell wide or short. Salvos that should have walked steadily onto target seemed to chase the American ships, always landing where they had been rather than where they were going. The escort carrier Kalinin Bay was hit by at least 15 8-inch and 14-inch shells. She should have been at the bottom of the Pacific within minutes. Instead, several shells passed completely through her unarmored hull without detonating, and she survived. Gambier Bay wasn't as fortunate. Concentrated fire from heavy cruiser Chikuma and Yamato's massive 18-inch guns finally crippled her at 0850. She capsized and sank, the only U.S. carrier ever sunk by naval gunfire. But it had taken over an hour of pursuit and hundreds of shells to kill a ship that had no business surviving the first salvo. What went wrong? Japanese fire control teams struggled with a gunnery problem that American radar could have solved in seconds. The targets were small, fast, and maneuvering aggressively. Visibility was poor, degraded by smoke screens and rain squalls that the Americans exploited ruthlessly. Japanese spotters had to rely on optical observation of shell splashes to correct fire, but the splashes kept disappearing in smoke or being mistaken for hits. The Americans, meanwhile, kept their accurate 5-inch fire on target using radar fire control. Those 5-inch guns, 40 times lighter than Yamato's main battery, scored hits on Japanese heavy cruisers because the American fire control systems could track maneuvering targets and automatically apply corrections. The Mark 37 gun fire control system directing the American 5-inch mounts was a marvel of automation. It could track targets in bearing, elevation, and range simultaneously. The Mark 12 and Mark 22 radars fed data directly into the Mark 1 ballistic computer, which continuously updated the firing solution. The guns responded automatically to the computer's commands through servo motors, no manual following of pointers, no delay between spotting a correction and applying it, just smooth, accurate fire that kept hitting Japanese ships while the Americans maneuvered wildly to avoid incoming salvos. Captain Yasuhiko Kurazumi, commanding the heavy cruiser Suzuya, later described watching American destroyer shells land with uncanny accuracy, while his own main battery struggled to find the range. The Americans seemed to know exactly where his ship would be when their shells arrived. They could shoot and maneuver simultaneously, maintaining accurate fire through radical turns that should have thrown off any fire control solution. Japanese gunners trained on systems that required steady courses for accuracy, found themselves outshot by ships a fraction of their size. The psychological impact was crushing. Center Force possessed overwhelming material superiority. Yamato alone displaced more than all of Taffy 3 combined. Yet, here they were, trading shots with escorts and escort carriers, taking damage from guns that shouldn't have been able to hurt them, and somehow failing to quickly destroy their vastly inferior opponents. Commander Setsuji Moriya, the same officer who had escaped the Iowa and New Jersey at Truk 8 months earlier, commanded the destroyer Nowaki during this battle. He had seen American radar fire control in action before, but watching it again, seeing American 5-inch shells consistently straddle his ship while his own fire control team struggled with optical spotting through smoke and spray, drove home a truth the Imperial Navy had been reluctant to accept. The Americans weren't just better equipped, they were playing a different game entirely. After over 2 hours of chaotic fighting, Kurita ordered a withdrawal. His ships had sunk 2 destroyers, a destroyer escort, and 1 escort carrier. They had damaged others, but they had also taken damage themselves, lost critical time, and failed to reach the vulnerable invasion transports in Leyte Gulf. Post-war analysis would reveal just how badly Japanese fire control had performed. Despite firing hundreds of large-caliber shells at essentially defenseless targets, Japanese hit rates were abysmal. Heavy cruisers didn't score hits on the escort carriers until the range had closed to 5 miles after an hour of pursuit. The world's largest battleship, mounting the most powerful naval guns ever built, needed sustained fire at diminishing ranges to sink a single escort carrier. American forces, fighting desperately for survival, had nevertheless demonstrated technological superiority that negated Japan's numerical and material advantages. Their radar fire control, their automated systems, their ability to maintain accurate fire while maneuvering, all of it combined to turn what should have been a massacre into a confused melee that ended with the Japanese withdrawing. Japanese officers couldn't fully understand what had happened. They knew American radar was good, but the gap between knowing that fact and experiencing its implications in combat was vast. A Japanese fire control team, no matter how skilled, no matter how well trained, was fundamentally limited by human reaction time and optical observation. An American radar fire control system operated at machine speed, processing information and updating solutions faster than any human team could match. It was as if one side was fighting with telegraphs while the other had telephones. Both could communicate, but the speed and efficiency were incomparable. The lesson should have been obvious after Samar, but Japan's industrial situation by late 1944 made correcting the radar gap impossible. They couldn't build enough reliable sets. They couldn't maintain the ones they had. They couldn't train sufficient personnel to operate complex electronics when those personnel were needed everywhere else. So they kept fighting with fundamentally inferior fire control systems against an enemy whose technological advantage only increased as the war progressed. Every surface engagement reinforced the same pattern. American radar fire control allowed them to shoot accurately at longer ranges, in worse conditions, while maneuvering aggressively. Japanese optical fire control required good visibility, steady courses, and time to observe and correct, time that American radars didn't give them. The human cost of this technological gap was measured in ships sunk, battles lost, and lives ended. But perhaps the deepest wound was psychological. Japanese naval officers had trained their entire careers, believing in the superiority of their doctrine, their skill, their dedication, discovering that none of it mattered when the enemy could see in the dark and hit targets beyond visual range. That revelation was almost harder to accept than the defeats themselves, because it meant they had been fighting blind from the start. When World War II ended, American intelligence teams fanned out across Japan, seeking to understand what the Japanese had known and when they had known it. Technical officers interviewed captured personnel, examined surviving equipment, and studied Japanese fire control doctrine. What they found was illuminating and sad. Japanese engineers had understood the principles of radar fire control. They had conducted experiments. They had built prototype systems. Some of these systems even worked, after a fashion, What they lacked was the ability to produce these systems in meaningful numbers and maintain them in combat conditions. Lieutenant Toshio Ota, a technical intelligence officer who survived the war, later documented his examinations of captured American radar equipment. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. His reports dripped with bitter admiration. Every component demonstrated manufacturing quality and engineering sophistication beyond Japanese capabilities. The radar units were precision-built, thoroughly tested, and came with detailed technical manuals and abundant spare parts. When American radar broke, technicians could repair it quickly using readily available components. When Japanese radar failed, which it often did, ships sometimes sailed for months, waiting for replacement parts that never came. The industrial disparity extended beyond just building the radars. American ships had trained radar operators, radar technicians, and comprehensive maintenance programs. Japanese ships that received radar often had crews with minimal training and no clear doctrine for employing the systems. The technology was new enough that many officers didn't trust it, preferring to rely on proven optical methods even when radar was available. This created a vicious cycle. Poor training led to poor results, which reinforced skepticism about radar, which meant continued reliance on optical methods, which kept Japan trapped in an outdated paradigm, while American radar systems improved with each generation. Captain Tameichi Hara, one of Japan's most successful destroyer commanders, wrote extensively after the war about the technological gap. He described watching American ships maneuver at night and in foul weather, with a confidence Japanese ships couldn't match. American commanders could charge through darkness at high speed, secure in their radar's ability to warn them of obstacles, land, or enemy ships. Japanese commanders had to slow down, post extra lookouts, and proceed cautiously, which meant that even simple navigation became an American advantage. They could move faster, react quicker, and position their forces more aggressively because their technology compensated for human limitations like night blindness and weather. But perhaps the most devastating revelation came from examining Japanese battle reports. Time and again, Japanese officers reported enemy ships appearing with suspicious foreknowledge of Japanese positions. They described American forces seeming to anticipate Japanese movements, arriving at intercept positions that suggested impossibly good intelligence. Some suspected spies or code breaking. They were partially right about the code breaking, but what they often didn't realize was that American radar was simply seeing them first. Surface search radar could detect ships at ranges of 20 to 40 miles, giving American commanders a comprehensive picture of the tactical situation before any visual contact occurred. This early warning allowed American forces to maneuver into advantageous positions while Japanese ships were still essentially blind. By the time Japanese lookouts spotted the enemy, American commanders had often been tracking them for an hour, planning their approach, coordinating their forces. It wasn't magic or supernatural skill, it was technology. But to officers trained to trust their eyes above all else, the effect seemed almost uncanny. The engagement at Truk, where Iowa and New Jersey had straddled Nowaki at 35,700 yards, became legendary in post-war Japanese naval circles. Not because it was a great battle, Nowaki escaped with only splinter damage, but because it demonstrated in the starkest possible terms what American radar fire control could do. To hit a small, fast-moving target at over 20 miles range, in combat conditions, with the first salvo, was something Japanese fire control could never have achieved. Their excellent optics could barely even see the target at that range, let alone track it accurately enough for gunnery solutions. Commander Moriya, interviewed after the war, described the experience as surreal. He had taken every evasive measure, zigzagging at maximum speed, but the American salvos kept finding him. He could see Iowa and New Jersey on the horizon, watch their guns fire, and then wait nearly a full minute for the shells to arrive. The time of flight at that range approached 60 seconds. Any normal evasion would have caused shells aimed at his original position to miss by hundreds of yards. But American radar was tracking Nowaki continuously, updating the firing solution in real time, compensating for his maneuvers before the shells even left the barrels. The shells still fell close enough that splinters peppered his ship's superstructure. He escaped only because Iowa and New Jersey were simultaneously chasing down other Japanese ships and couldn't devote sustained fire to a single destroyer. But the message was clear. Japanese ships could run, but they couldn't hide. American radar would find them, track them, and engage them at ranges where Japanese optical fire control was useless. The psychological impact on Japanese naval personnel who experienced these engagements was profound. They had been trained to believe in the superiority of Japanese night-fighting doctrine, in the power of optical excellence, in the skill born from rigorous training. Discovering that all of this meant little against an enemy with fundamentally superior technology created a sense of futility that no amount of courage could overcome. By mid-1945, surviving Japanese surface ships largely avoided American forces, not from cowardice, but from cold calculation. Engaging American warships meant fighting at a technical disadvantage so severe that tactical skill became irrelevant. Better to preserve ships and crews for the final defense of the home islands than waste them in one-sided engagements, where American radar fire control would pick them apart from beyond visual range. The war ended before that final defense became necessary. But the lesson remained. Naval warfare had fundamentally changed. Radar had done to surface combat what aircraft carriers had done to battleship duels. It hadn't made traditional skills obsolete exactly, but it had subordinated them to a new technology that rewrote the rules of engagement. Today, modern warships carry radar systems that would seem like science fiction to 1940s engineers. Phased array radars that can track hundreds of targets simultaneously, fire control systems that engage multiple threats with missiles traveling at hypersonic speeds. All of it descended from those early Mark 8 and Mark 13 radars that gave Iowa and New Jersey their seeing beyond sight capability. But the fundamental principle remains unchanged. In naval warfare, the side that can detect, track, and engage first holds an almost insurmountable advantage. The Japanese learned this lesson the hardest way possible, through defeats that their courage and skill couldn't prevent, because they were fighting opponents who could see when they were blind and shoot accurately when they could barely aim. When American battleships like Iowa opened fire at 35,000 yards and straddled their targets, they weren't just demonstrating superior technology. They were announcing the arrival of a new era in naval combat, an era where human excellence, while still necessary, was no longer sufficient, where technological superiority could negate traditional advantages like heavier guns or thicker armor, where the invisible radio waves bouncing off enemy ships mattered more than the visible flames of muzzle blasts. The Japanese Navy never expected this reality. They had prepared for a war of optical rangefinders and carefully aimed salvos, of night torpedo attacks and aggressive surface actions. What they got was an enemy that could hit what it couldn't see, maneuver while maintaining fire, and operate effectively in conditions that reduced Japanese forces to blind shooting. The Iowa-class guns that straddled Nowaki at over 20 miles. The radar sets that allowed Washington to slaughter Kirishima in darkness. The fire control systems that let tiny destroyers hit Japanese cruisers while dodging salvos. All of it was part of a larger revolution that Japan couldn't match and couldn't overcome. And when the war ended, when Japanese officers finally saw the full extent of American radar capabilities, their shock was complete. They hadn't just been outfought, they had been operating in a different technological universe. The Americans had been playing three-dimensional chess while Japan was still thinking in 2 dimensions. That realization, more than any single defeat, more than any lost battle, defined the true gap between the two navies. Not a gap in courage or skill or dedication. A gap in industrial capability, in technological sophistication, in the ability to turn scientific principles into reliable combat systems. A gap that radar fire control made visible in the most brutal way possible, through shells landing where they shouldn't have been able to, through hits scored in impossible conditions, through engagements where the Americans could shoot and the Japanese could only die. This was the true story of naval radar fire control in the Pacific War. Not just a technological advantage, but a fundamental redefinition of what was possible in naval combat. The Japanese dismissed American radar at first, considering their optical systems superior. By the time they understood their error, American battleships were hitting targets at 20 miles, and there was nothing Japan could do to close that gap. November 15th, 1942. Just after midnight in the pitch-black waters north of Guadalcanal, Rear Admiral Willis Lee stood on the bridge of USS Washington, studying the radar screen that showed what his eyes couldn't see: Japanese ships, a lot of them, including the battleship Kirishima. Lee was the Navy's foremost expert on radar. He understood the technology better than almost any flag officer in the fleet, and tonight that knowledge was about to save American lives and doom a Japanese battleship that had no idea what was coming. The night action off Guadalcanal would become the first time in history that a battleship sank another battleship using radar fire control in complete darkness. No searchlights, no star shells, no optical rangefinders straining to pick out a silhouette against the night sky. Just radio waves painting targets on screens, while computers calculated firing solutions faster than any human could. It was a preview of a new kind of naval warfare, one where darkness was no longer an ally but just another condition that American technology could overcome. Washington's companion, USS South Dakota, had already taken heavy punishment. An electrical failure knocked out her radar and communications, leaving her silhouetted against burning American destroyers. Japanese searchlights locked onto her. Shells rained down on her superstructure. Fires blazed. South Dakota was in serious trouble. But that catastrophe created an opportunity. While every Japanese gun and searchlight focused on South Dakota, Washington remained undetected in the darkness. Her radar tracked Kirishima and the surrounding Japanese ships with perfect clarity. Lee waited, watched the range close. Let the Japanese concentrate all their attention on the burning South Dakota. And then, at 8,400 yards, Washington opened fire. The first salvo struck Kirishima. The second salvo hit her again. Shell after shell slammed into the Japanese battleship at a rate she couldn't match or even understand. Washington's Mark 8 fire control radar was spotting the fall of her own shells, allowing instant corrections. Her Mark 8 rangekeeper was maintaining the firing solution even as both ships maneuvered. 9 16-inch shells out of 75 fired found their target, a 12% hit rate in total darkness. Over 45-inch shells also struck home. Kirishima's superstructure was wrecked, her steering damaged, fires spreading uncontrollably. She was dying. Japanese lookouts on Kirishima finally spotted Washington's muzzle flashes and reported the presence of another American battleship. But by then, it was too late. They couldn't see the target well enough for accurate return fire. Their optical fire control was useless in the darkness. They fired back desperately, shells falling wide or short. Not a single hit on Washington. She maneuvered to avoid torpedo attacks, kept firing, kept hitting. By 00:15, Kirishima was a blazing wreck. At 00:30, with his bombardment mission impossible and his flagship crippled, Admiral Kondo ordered a general withdrawal. Kirishima was scuttled by her own crew hours later, sinking in the same waters where so many other ships had died during the Guadalcanal campaign. The contrast between the two battleships' performance that night told a story that would echo through the rest of the war. Washington had fought an entire enemy force in complete darkness and emerged undamaged, sinking a battleship and driving off the rest. She could do this because her radar allowed her to see when the enemy was blind, shoot accurately when they were guessing, and maneuver with confidence when they were groping through darkness. Kirishima and her escorts had fought bravely but uselessly. Their excellent optical systems meant nothing when there was nothing to see. Their skilled fire control teams couldn't hit what they couldn't track. The technology gap had turned what should have been a confused melee into a one-sided slaughter. Admiral Lee's success off Guadalcanal was so dramatic that it forced the Japanese Navy to confront an uncomfortable truth. American radar wasn't just better, it was fundamentally changing the nature of naval combat. Night battles had always favored the bold and the skilled. The Japanese had trained extensively for night fighting, developing tactics and techniques honed through years of practice. But all of that training assumed both sides were operating under the same limitations. Fighting in darkness, where optical range-finding barely worked, where fire control was as much art as science, where courage and aggression could overcome material disadvantages. American radar fire control eliminated those assumptions. Washington had fought as effectively at night as most battleships could fight at noon. Better, actually, because her radar wasn't affected by smoke, muzzle flash, or the confusion of battle. The psychological impact on Japanese naval officers who studied the engagement was profound. If Americans could fight at night with radar-directed guns, then one of Japan's key tactical advantages, their night fighting doctrine, had been neutralized, maybe worse than neutralized, because now darkness favored the side with better radar. This realization shaped Japanese thinking for the rest of the war. They knew American radar was superior. What they struggled to accept was how completely that superiority had changed the tactical calculus. Every engagement plan, every operational order, every strategic assumption had to account for American ships that could see in the dark, shoot accurately beyond visual range, and maneuver with confidence in conditions that left Japanese forces essentially blind. It was like fighting opponents who could read your mind. Everything you tried to hide, every clever maneuver, every attempt at surprise, rendered useless by technology that simply saw through it all. The Battle of Surigao Strait, nearly 2 years later, would drive home the lesson with even greater finality. October 25, 1944. The same night, Taffy 3 was fighting for survival off Samar. Another Japanese force was attempting to break into Leyte Gulf from the south. Vice Admiral Shoji Nishimura commanded 2 battleships, 1 heavy cruiser, and 4 destroyers. His mission was to transit Surigao Strait in darkness and fall upon the American invasion fleet at dawn. Simple in concept, suicidal in execution. Rear Admiral Jesse Oldendorf waited at the northern end of the strait with 6 old battleships. 5 of them were survivors of Pearl Harbor, raised from the mud and rebuilt. West Virginia, California, Tennessee, Maryland, Mississippi, and Pennsylvania. These were supposed to be obsolete, slow, outdated, relics of a bygone era being used for shore bombardment because they couldn't keep up with the fast carrier task forces. But 3 of them, West Virginia, California, and Tennessee, had been completely rebuilt with the latest Mark 8 fire control radar, and that made all the difference. At 0302, West Virginia's radar detected Nishimura's force at 42,000 yards, nearly 24 miles. In total darkness, the radar operators watched the blips close, tracking speed and bearing with precision. By 30,000 yards, the fire control teams had a complete firing solution. They knew the target's range, course, speed, even the angle at which she was approaching. All of this calculated automatically by the Mark 8 rangekeeper, updated continuously as the enemy closed. The Japanese had no idea they'd been detected. No idea that American battleships were tracking them from beyond visual range. No idea they were sailing into a perfectly prepared trap. At 0353, at a range of 22,800 yards, West Virginia opened fire. Her first salvo struck the Japanese battleship Yamashiro, in darkness so complete that Japanese lookouts couldn't see the American ships even after their guns fired. California and Tennessee joined in 2 minutes later. The 3 battleships with Mark 8 radar proceeded to demonstrate what modern fire control looked like. They fired salvo after salvo with mechanical precision, corrections applied automatically based on radar spotting of shell splashes, firing solutions updated continuously, guns trained and elevated by servo motors responding to computer commands faster than any human crew could match. The Japanese couldn't fight back effectively. They could barely see their targets. When they did spot muzzle flashes, the extreme range and poor visibility made accurate return fire impossible. Yamashiro and the heavy cruiser Mogami were hit repeatedly. Shells tore through armor, started fires, knocked out systems. The Japanese ships tried to maneuver, tried to close the range where their optics might work, tried desperately to bring their own guns to bear, but American radar tracked every move. The firing solutions adjusted instantly. The shells kept landing. West Virginia alone fired 93 16-inch shells. California fired 63 14-inch rounds. Tennessee fired 69 14-inch shells. Maryland, equipped with the older Mark III radar, managed to get off 48 16-inch shells by ranging on West Virginia's splashes. Mississippi fired a single salvo. Pennsylvania never found a target. The three ships with Mark VIII radar did essentially all the work, and they did it in under 15 minutes. At 0419, Yamashiro capsized and sank, taking Admiral Nishimura and most of her crew with her. Mogami, crippled and burning, managed to limp away only to be finished off by air attack later that day. The Battle of Surigao Strait was over before it really began. The last battleship versus battleship engagement in history had been a demonstration of technological dominance so complete that Japanese forces never had a real chance. They'd sailed into a strait where American radar could track their every move, where fire control systems could hit them from ranges their own systems couldn't even measure accurately, where the darkness that should have protected them instead became their shroud. It wasn't a battle. It was an execution. What makes Surigao Strait particularly devastating is that the American battleships weren't even their best ships. These were the old, slow battle wagons, the Pearl Harbor survivors, ships that would have been considered obsolete if not for extensive rebuilding programs. Yet armed with Mark VIII radar fire control, they'd destroyed a Japanese force without taking a single hit themselves. The technology had transformed second-line ships into unstoppable killers. Imagine what the fast battleships like Iowa could do with the same systems. Japanese post-war analysts struggled to find any tactical lessons from Surigao Strait that might have changed the outcome. Better formation? Irrelevant when the enemy could track you from 24 miles away. More aggressive maneuvering? Pointless when radar could follow every turn. Faster approach? Just meant dying quicker. The fundamental problem wasn't tactics or training or courage. It was that American ships could fight in conditions where Japanese ships were effectively blind. No amount of tactical brilliance could overcome that handicap. The engagement also highlighted another crushing advantage. American ships could maneuver freely while maintaining accurate fire. Admiral Weyler, commanding the battle line, actually ordered course changes during the engagement to improve firing positions. The ships turned in formation, adjusted speed, repositioned themselves, all while their guns continued hitting targets. The Mark VIII fire control system with its gyroscopic stabilization compensated for the ship's movements automatically. Japanese fire control required steady courses for accuracy. Every time a Japanese ship maneuvered to evade, her fire control solution degraded. American ships could shoot and dodge simultaneously. Japanese ships had to choose one or the other. This ability to maintain fire during maneuvers proved decisive in multiple engagements. It meant American ships could respond to torpedo threats, adjust positions for better firing angles, or reposition to unmask batteries, all without interrupting their fire. Japanese ships that maneuvered lost their firing solutions and had to re-establish them manually. By the time they steadied on a new course and recalculated, the tactical situation had changed. American ships never faced that dilemma. Their automated systems tracked targets continuously, regardless of own ship motion. The war ended in August 1945. When American occupation forces arrived in Japan, they found naval personnel still struggling to understand what had happened. Technical officers examined captured American radar equipment with something approaching despair. The precision, the reliability, the integration with fire control systems, all of it represented a level of sophistication Japan hadn't approached. One Japanese radar engineer, examining a captured Mark XIII fire control radar, noted that even if Japan had obtained the complete technical specifications in 1941, they lacked the industrial capacity to produce them. That single observation captured the entire tragedy of Japan's technological position. It wasn't a matter of stealing designs or copying equipment. The problem went deeper. American radar worked because it was backed by an industrial system that could manufacture complex electronics to tight tolerances, test them thoroughly, produce them in quantity, supply spare parts, and train personnel to maintain them. Japan lacked that industrial foundation. Building a few prototype radars in laboratories was achievable. Equipping a fleet with thousands of reliable combat-ready sets was beyond Japanese capabilities. The disparity showed in maintenance records. American ships had radar technicians, comprehensive technical manuals, diagnostic equipment, and supply chains providing replacement parts. When radar broke, which it often did given the mechanical stress of naval gunfire, American technicians could usually fix it within hours. Japanese ships that received radar often had it break within weeks and stay broken for months, waiting for parts that never came. A few Japanese ships eventually received moderately effective radar sets by late 1944, but by then they were facing American forces whose radar technology had advanced another generation. It was like showing up to a gunfight with last year's pistol when your opponent has this year's rifle. The human element made the technological gap even wider. American radar operators received extensive training. They practiced tracking targets, distinguishing false returns from real contacts, maintaining equipment, troubleshooting problems. The training programs produced specialists who understood both the technology and its tactical applications. Japanese radar operators, when they existed at all, often received minimal instruction on hastily installed equipment with inadequate documentation. They were expected to operate systems they barely understood with no maintenance support. This created a feedback loop of failure. Inadequate training led to poor performance, which reinforced officer skepticism about radar's value, which resulted in continued reliance on optical systems, which meant continued failure to develop effective radar doctrine, which meant more defeats. American forces, by contrast, used each engagement to refine their radar employment, developing new techniques and passing lessons throughout the fleet. The gap widened with every battle. By war's end, American surface forces operated with such confidence in their radar fire control that night engagements held no terror. Darkness was just another condition, handled by technology with the same efficiency as daylight. Japanese forces, lacking equivalent systems, found night operations increasingly desperate. They couldn't hide in darkness when American radar could see them. They couldn't fight effectively when their optical fire control was useless. Night actions, once a Japanese strength, became another American advantage. The transformation was complete. At the start of the Pacific War, Japan had expected their superior night fighting doctrine and excellent optical systems to provide tactical advantages. By war's end, American radar fire control had not only negated those advantages but reversed them entirely. The Americans could see in the dark, the Japanese could not. Wars are often decided by such asymmetries. The side with better intelligence wins. The side with longer logistics succeeds. The side with superior technology dominates. Radar fire control was all three. It provided intelligence by detecting enemy ships before they could detect you. It extended logistics by allowing ships to navigate and fight in any conditions. It demonstrated technological superiority so overwhelming that no amount of bravery or skill could compensate. Looking back from the present, it's easy to see radar fire control as inevitable. Of course, the side with better electronics won. Of course, technology triumphed over tradition. But for Japanese naval officers living through these defeats, the experience was bewildering and demoralizing. They'd trained their entire careers for one kind of warfare, only to discover the rules had changed completely. Skills they'd honed through decades of practice became irrelevant overnight. Equipment they'd trusted absolutely revealed itself as obsolete. Doctrine they'd refined through bitter experience proved useless against opponents operating in a different technological paradigm. The shock was similar to what cavalry officers experienced when machine guns made mounted charges suicidal, or what battleship advocates felt when aircraft carriers proved dominant. Technologies that change the fundamental nature of warfare always leave some people behind. The tragedy for Japan was that they saw it coming and couldn't stop it. They knew American industry was more advanced. They knew American electronics were superior. They understood that radar would be important. But knowing something intellectually and experiencing it in combat are vastly different. The knowing didn't prepare them for the reality of American shells landing accurately from beyond the horizon. for engagement ranges that exceeded anything optical systems could match, for night battles where the Americans fought as if it were daylight while Japanese forces groped through darkness. That gap between knowing and experiencing defined Japan's naval war in the Pacific. They knew they were outproduced. Experiencing it meant watching American fleets grow larger while Japanese forces dwindled. They knew American logistics were better. Experiencing it meant running out of fuel while American ships operated freely. They knew American technology was advancing. Experiencing it meant radar-directed shells landing with impossible accuracy from impossible ranges. Knowledge without the capacity to respond is just another form of helplessness. The story of Japanese forces encountering American radar fire control is ultimately a story about industrial capacity. Not genius versus genius. Not courage versus courage. But system versus system. America's industrial might allowed them to develop, produce, and field radar fire control systems that worked reliably under combat conditions. Japan's more limited industry could not. That difference, more than any tactical brilliance or strategic insight, determined the outcome of the Pacific Naval War. American ships hit what they couldn't see because American factories built radar that worked. Japanese ships couldn't return fire effectively because Japanese industry couldn't match that capability. When Iowa and New Jersey straddled Nowaki at 35,700 yards, they weren't demonstrating superior seamanship or better training. They were demonstrating superior manufacturing. The radar on those battleships represented thousands of hours of engineering work, millions of dollars of industrial investment, and supply chains stretching across an entire continent. The shells landed where they did because every component in the fire control system worked exactly as designed, tested by quality control systems that rejected anything imperfect, maintained by trained technicians with adequate parts, operated by personnel who understood the technology thoroughly. Japan couldn't replicate any of that. The gap wasn't in knowing how, it was in being able to do. And so Japanese ships kept dying. Kept fighting battles where American radar saw them first, tracked them accurately, and directed fire that landed with precision they couldn't match. Kept losing engagements where their courage and skill meant nothing because the technological advantage was simply too great. The Americans could hit targets at 20 miles. The Japanese, relying on optical systems that worked out to maybe half that range in perfect conditions, were fighting blind. By the time they could see American ships clearly enough to engage effectively, American shells were already falling. The battle off. Samar showed this perhaps more clearly than any other engagement. Japanese battleships and cruisers, vastly superior in size and firepower to the American escorts they were chasing, couldn't land hits consistently because their fire control couldn't track the small, maneuvering targets through smoke and rain. Meanwhile, American destroyer guns, a fraction of the size, scored hit after hit using radar fire control that simply worked. Technology mattered more than tonnage. Systems mattered more than steel. That lesson extends far beyond World War II. In modern warfare, technological superiority often trumps traditional measures of military power. Numbers matter less when quality is dominant. Training matters less when systems compensate for human limitations. Doctrine matters less when the enemy is operating under entirely different rules. American radar fire control in the Pacific War was an early example of what would become a pattern in modern conflict. The side with better information systems wins. The side with better sensors dominates. The side whose technology works reliably under combat conditions prevails. Japan learned this lesson the hard way, through defeats that their bravest efforts couldn't prevent and their most skilled commanders couldn't reverse. All because American battleships could see in the dark, shoot beyond the horizon, and hit targets that Japanese optical systems couldn't even detect. The radar made the difference, and Japan, despite knowing how important it was, could never close the gap. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.